I am Madison P. Munar, Assistant Professor at the Department of Biological Sciences, College of Science, Central Luzon State University. The title of my presentation is Microbiological Synthesis of Tellurium Nanocrystals by 3 new bacterial strains isolated from marine sediment enrichment culture. This study was conducted at the Department of Molecular Biotechnology, Graduate School of Advanced Sciences of Matter, Hiroshima University, Japan. I will start my presentation with a brief introduction on microbial tellurite bioremediation and tellurium recovery, after which I will present the isolation and characterization of the 3 new bacterial strains. Insights on bacterial tellurium recovery will be presented, and I will end my presentation with a brief summary. Tellurium is mostly recovered from copper mine tailings. The amount of extracted tellurium in a copper concentrate is generally below 100 parts per million. Significant increase in the market demand for tellurium encouraged some countries to search for new possible deposits of tellurium. Top global producers of tellurium are Europe, China, and Japan. Tellurite is highly toxic to most microorganisms. Tellurite generates superoxide radicals, which interferes with biological function of biomolecules, leading to cell death. Studies on microbial recovery of tellurium reported several bacterial genera with tellurite resistance and reduction activities. Among these are Bacillus, Escherichia, Pseudomonas, Rhodobacter, and Shewanella. Microbial cell-mediated tellurite bioremediation and tellurium recovery offers a viable alternative as cleaner and sustainable technology to solve tellurite pollution and overcome tellurium resource scarcity. Tellurium is used in photovoltaic cells, rechargeable batteries, compact discs, and as quantum dots for cancer diagnosis and treatment. This study aims to isolate bacterial strains with tellurite bioremediation and tellurium recovery potential from marine sediment enrichment culture. The marine sediment used in this study was provided by Dr. Takeshi Terahara of the Tokyo University of Marine Science and Technology. The marine sediment was collected at a depth of 100 meters off Niigata Bay, Japan. The marine sediment was cultivated in RCVBN medium under continuous illumination. The culture showed prominent growth of a photosynthetic purple sulfur bacterium, Maricromatium sp, which is a tellurite-reducing bacterial strain. The marine sediment enrichment culture showed tellurite reduction activity up to 10 millimolar sodium tellurite. Tellurite reduction activity was prominent at pH 9 and pH 10. 8 bacterial species were identified in the enrichment culture using genus-specific primers. This includes Maricromatium, Desulfovibrio, Pseudomonas, Enterococcus, Oceanotoga, Sunsiokinia, Vibrio, and Shewanella. Pour plating method was used to isolate culturable tellurite-reducing bacteria from the marine sediment enrichment culture. Plates grown at 37 degrees Celsius showed visible isolated colonies after 24 hours incubation. 3 distinct colonies of gram-negative bacteria were isolated using the streak plating method. Full-length 16S rDNA was amplified, cloned, and sequenced from the 3 pure cultures. Blast search using the 16S rDNA sequences revealed 99% homology with 0.00 E value to Shewanella algae, Pseudomonas pseudoalkali and Pseudomonas stutzeri. Phylogenetic analysis suggested novel strain status. These new strains were designated as Hiro-1, Hiro-2, and Hiro-3 respectively. The new isolates showed similar colony morphology and TR activity with the type cultures. S. algae Strain Hiro-1 formed colonies with round form, entire margin, convex elevation, mucoid consistency, and orange color. P. pseudoalkali Strain Hiro-2 formed colonies with irregular form, undulate margin, raised elevation, viscid consistency, and translucent color. P. stutzeri Strain Hiro-3 form colonies with wrinkled form, undulate margin, raised elevation, rugose consistency, and yellow color. S. algae Hiro-1 and P. stutzeri Hiro-3 grew optimally at pH 7, while P. pseudoalkaligenes Hiro-2 grew optimally at pH 9. The new isolates are marine mesophilic bacteria. The three new strains are facultative anaerobes. Optimum tellurite reduction activity coincided with optimum pH for growth on respective strains. Gradual tellurite reduction was observed in the three new strains. S. algae Hiro-1 showed the highest resistance and reduction activity at 15 millimolar sodium tellurite. Both Pseudomonas strains showed resistance and reduction activity at 4 millimolar sodium tellurite. Intracellular tellurium crystals were observed on the three new strains using transmission electron microscopy. Tellurium crystals in S. algae Hiro-1 showed long needle crystals, which annealed together forming Te rosettes, possibly through electrostatic interaction. P. pseudoalkaligenes Hiro-2 showed small needle crystals, while P. stutzeri Hiro-3 showed Te nanorods. The minimum unit size of tellurium crystals is 60 nanometers. Both Hiro-2 and Hiro-3 showed tellurium nanocrystals scattered within the cell cytoplasm. Intracellular crystal formation denotes influx of metal ions into the cell cytoplasm. Thus, unknown metal ion transporters or channels might be involved in this phenomenon. Once inside the cell, enzyme-catalyzed reduction of tellurite ions into elemental tellurium precedes crystal nucleation and growth. Tellurium recovery on new bacterial strains was investigated using inductively coupled plasma-optical emission spectroscopy. Highest recovery was recorded in the original marine sediment enrichment culture with 72% recovery at pH 9, followed by P. pseudoalkaligenes Hiro-2 with 58% recovery at pH 7. There is no significant difference on tellurium recovery at pH 9 in the three new bacterial strains with less than 40% recovery. The three new bacterial strains identified in this study effectively reduced tellurite even at high concentrations above 1 millimolar sodium tellurite and may be useful for tellurite bioremediation. This reduction occurs within the cell, but determining the exact mechanisms will require further study. These new strains showed species-specific tellurium crystal morphologies and has the potential for the recovery of this valuable metalloid to augment tellurium resource scarcity. I would like to acknowledge Hiroshima University for providing my PhD scholarship under the Top Global University Project MEX Scholarship Japan, and to Dr. Takeshi Terahara for providing the marine sediment used in this study. Thank you very much for your attention.